technical problem straight away. Is that on the projector? Okay, so thanks, Andres. So I'm Graham Hutton from the University of Nottingham, and the subject of my talk today is calculating correct compilers, which is based on joint work with Patrick Barr from Copenhagen. And the picture here is supposed to illustrate someone doing a really simple calculation, 1 + 1 = 2, and as we'll see, that's what this talk is really about, trying to do simple calculations. So let's start off with a bit of background and a bit of fun, because it's 9 o'clock in the morning. So how do you make sausages? So what you do to make sausages is you take some source material, so here he is, or you can have a vegetarian alternative if you prefer, and what you do is you feed him into a sausage machine, which is here, and you turn the handle, and out the other side hopefully pops some sausages. And the point here is that this is a systematic mechanical process. You put something in one side, your pig on the left, and you turn the handle, and hopefully out the other side pops something that you're interested in, which in this case is some sausages. Okay, so sausage machine, remember this, we'll come back to this many times. So how do you make compilers? So a compiler is something like GHC. It takes a high-level program in as an input, and it translates it down to an equivalent low-level program. And what I'd like to do is have a sausage machine for making compilers. So I'd like to put, rather than a pig in the left-hand side, I'd like to put a description of a programming language. And you can see here I've used the same color. It doesn't show up very well here, but this is a pink programming language. And then what I want to do is have some kind of sausage machine, and actually the sausage machine here is me, or Patrick, or maybe some of you if you get interested in this kind of stuff. And we turn the sausage machine handle, and out the other side, hopefully, comes a compiler which implements this language. So this is the idea of the talk. I want a sausage machine that lets me, in a systematic, mechanical kind of way, translate programming language descriptions into compilers which implement them. Okay, so that's the name of the game. So that's the high-level message. So what I'd like to do in the next 45 minutes or so is present to you a new approach to the problem of calculating compilers from high-level semantics. So what I want to do is start with a high-level semantics for a programming language, and then in a series of steps, derive or calculate a compiler which correctly implements that semantics. Okay, that's the name of the game here. Everything which I'm going to show you is in the end going to be quite simple. There's no fancy types, there's no fancy machinery, it's just simple Haskell 98 and equational reasoning. And all the calculations, so I'm going to do them by hand. I like to do them by hand on pen and paper. My co-author, Patrick, he likes to do them in a proof assistant. So he does all this stuff in the Coq theorem prover. So you can either do this stuff by hand, or you can do it in a proof assistant if you like. So I'm going to show you this for a trivially simple programming language. If you've seen any talks from me before, or you've read any of my papers, you know what this language is going to be. It's the language of integers and addition. And this has got just enough computational structure to study all sorts of things. And I've written many papers, and there's various things in the book about it as well. It's a trivial language, but it's a really good setting to study interesting computational phenomena. So I'm going to show you in a series of steps how to calculate a compiler which implements simple arithmetic expressions, just built up from integers using addition. But everything which I'm going to show you does scale to more sophisticated settings. So in particular, if we considered a language which had exceptions, or a language which had state, say local state or global state, or variable binding, call by value, call by name, call by need, loops, so for loops or while loops, non-determinism, interrupts, or any kind of combinations of these features, every time we tried our sausage machine and we turned the handle, it just worked. Okay, so I'm going to show you it for a very, very simple language, but the take-home message here is that this does scale to more sophisticated settings as well. And I'll come back to that at the end of the talk as well. So here is the language which we're going to consider. It's the simple language of arithmetic expressions. So here's the syntax of the language and the semantics. And I know not everyone here is a Haskell expert, so I'll talk through everything on my slides very, very, very slowly. So here's my syntax. So I'm describing, or I'm declaring, a Haskell data type for simple arithmetic expressions. And there's only two constructors in the data type. We have a val tag, which takes an integer as a parameter, and we have an add constructor, which takes two sub-expressions. So this declaration is declaring three things. It's declaring a new data type called expr, and it's declaring a val constructor, which takes an integer argument, and an add constructor, which takes two sub-expressions as arguments. So it's just a simple data type of arithmetic expressions comprising integers and addition. And then the meaning or semantics of this data type is given by a little evaluation function. And it's just a trivial little recursive function. So it takes as input an expression, and it delivers as output its integer value. And it's just kind of first-year undergraduate level stuff, simple recursive definition. If I evaluate a value, I get the underlying value. And if I evaluate an addition, I evaluate the first thing, x, I evaluate the second thing, y, then I've got two integers, and I add them together, and I'm done. Okay, so this is our starting point. This is our language description, which we want to feed into our sausage machine. Okay? So just to make sure everyone's okay with this, because, again, not everyone in the room is a Haskell expert. Some are just starting out with Haskell. If I took a concrete expression, such as 1 plus 2 plus 3, bracketed to the right, here's how I could represent it as a value in this expression data type. So I just got a whole bunch of val tags, a couple of adds, and it's represented like that. So it's essentially the same structure. There's just a bit of syntactic noise in there because we're writing it as a value in this data type rather than as a piece of concrete syntax. And then, of course, if I evaluated that expression, I would get the expected result. I would get the integer 6. Okay? So let's start with our first sausage machine. We're going to build 3 sausage machines, and then we're going to see how we can make 1 sausage machine out of them in the end. So I'm going to show you how to calculate a compiler for this language in 3 steps. And the first step is that I'm going to make the manipulation of arguments explicit. Okay, so what do I mean by this? Well, if I look back to my semantics, imagine you're at the point when you're executing this addition down the bottom. Where do the arguments live? Okay, so that's Simon's business. They live somewhere in the GHC runtime. Okay, you don't see explicitly in the text of this definition where these arguments actually live. And the process of calculating a compiler is making implicit things, like the manipulation of the arguments, explicit. Okay, so we want to make implicit things in this simple semantics here explicit, and that's really the key to evolving a compiler. So the first thing we're going to make explicit is the manipulation of arguments. So we're going to do this by transforming the semantics to use a stack. Okay, so I'm going to set this up as a little puzzle or goal which we're trying to solve. So the aim here is that we want to define a new semantics which introduces the idea of manipulating arguments using a stack. Okay, so let's understand the type first of all. So the type says, well, we've got a new function called eval prime because it's a new semantics, and it takes an expression as input as before, but it no longer now just returns an integer. Now it takes a stack as an input, and it gives back a stack as a result. And a stack here is just a list of integers. Okay, and the convention is that the first thing in the list is the top of the stack. Okay, so that's our type. And the behavior we'd like of this function is specified by the little equation at the bottom. So it's very simple to understand. It says, if you give my new semantics an expression E and a stack S, what I want is that I'll get the same stack back as I started with, except I'll have one extra value sitting on top of the stack, and that's the value of that expression. Okay, so now we've got a problem that we're trying to solve, or a puzzle we're trying to solve. So what you would typically do at this point is just say, well, this is a trivial little problem. You just define the evaluation function, eval prime, and maybe prove that it satisfies this, or quick check it, or just kind of convince yourself that it satisfies it. But I want to calculate this. I don't want to cheat. I don't want to use any kind of pre-knowledge. I want to evolve the definition of this function from the desire to solve this equation. And this is what I mean by calculation. So it's just like at high school when you're given a kind of algebraic equation and you've got some knowns and you've got maybe an unknown and you want to solve for the unknown. And it's exactly the same here. I've got one known here, which is the definition of the eval function that's given to me. That's the input to my sausage machine. And what I want to do is evolve in a systematic way the unknown, which is the new semantics eval prime. And there's a really simple way to do this. You just try and prove this equation using normal induction and then out of that proof actually falls the definition of this function. Okay, so the base case is really simple, so I won't show you that one. I'll show you the inductive case, and I'll get you to help me as we go along as well. So what I want to do is try and prove that this equation is true for the case when E is an addition. So it's add of xy. And we'll see that the goal of kind of proving that it's true actually gives us the definition of the function. Okay, so let's try and see this, see how this works out. So here's the case for addition. So I'll start on the left-hand side. I'm trying to work out what eval prime of add xys is. Okay, so I'm going to do a little calculation here. The talk's called Calculating Correct Compiler, so I have to show you a calculation. This is the only calculation I'm going to show you in the whole talk. And I'm going to get you to help me with it as well. Okay? So here's the starting point. What can I do from this point? I'm starting to turn my sausage machine handle. What's the only thing I could really do at this point? Any ideas? Expand add. Well, add's a constructor, so I can't expand that. Any other ideas? Yeah, I can use the specification, because the specification says that function better satisfy this equation. Okay, so let's just assume it does for now, and that will allow us to make a first step of progress. So the specification allows us to rewrite it like that. It's saying if I evaluate an addition, I better get the result of actually evaluating that addition sitting on top of the stack. Okay, what's the obvious next step now? There's only one thing I can do. Evaluate, okay? I turn my sausage machine handle one step more. So I can apply the definition of eval. I know how to evaluate and add. I just evaluate x plus evaluate y. So I turn my handle one more time, and I get down to here. Okay, any ideas what we should do now? Can we expand any more definitions? No, because there's none left. But what have we got at our disposal now to make further progress? Remember what kind of proof we're doing. What could we do? Okay, we're doing an inductive proof. So we can assume that the property we're trying to prove is true for the arguments x and y. Okay, so we can assume the eval prime of x for some stack s is eval of x for some stack, and similarly for y. Okay, so what we'd like to do is get this thing into the form where we have eval of x sitting on some stack and eval of y sitting on some stack, and then we can apply our induction hypothesis. But we haven't quite got that at the moment. We've got eval of x plus eval of y sitting on a stack. So we need to tease it apart a little bit. So this is the point where we introduce a little helper function to get this thing into the form where we can actually make some progress. And this is, we're kind of driven here by the desire to apply the induction hypotheses. So here's a little helper function, which is going to make things possible. So I define a little helper function called add, and it takes a stack with at least two things on the top, n and m, and it takes them off, flips them over, because usually things are on the stack in the wrong order, and adds them together and puts their sum back on. And this is a good helper function to define, because if I use this, it allows me to tease this apart into exactly the right form that I need to apply my induction hypotheses. Okay? So if I read this way, if I do add of eval of y colon eval of x colon s, and I apply my little add function, I'll get exactly up to here. Okay? And I can do this either way around. And this was a good thing to do, because now I can apply my induction hypothesis. By induction, this bit, eval of x colon s, is the same as eval prime of x and s. And then I can do the same with eval of y. Eval of y, const onto any old stack, doesn't matter what it is going to be eval prime of y and that stack. Okay? And what we've actually done here is calculated the definition of this recursive function in the add case. Okay? So here's where we are. What we've done is we've turned the sausage machine handle one step around, and we've taken our original evaluation function and we've transformed it into a version which manipulates arguments using a stack. Let's make sure we all understand this. So the type says it takes an expression in and a stack in, and then gives us a stack out. And the base case, which we didn't calculate, but it's very simple to do so, the base case says if we evaluate a value and we've got a stack, all we do is push that value onto the stack. And again, we have another little helper function here called push, which puts the number onto the top of the stack. And then the case we just calculated, and we did this just by turning the handle. We didn't need to know anything. We didn't need to know what we were aiming for. We just used the desire to solve the equation to derive the definition or calculate the definition. So you kind of read this backwards. Eval prime of an addition is you first of all evaluate the first argument, and that will leave it on top of the stack. Then you evaluate the second argument. That will leave that on top of the stack. And then you'll have at least two things on the stack, and you add them together. Okay, so this is the first step in evolving a compiler. So, step 2. Now we're going to make the flow of control explicit. Okay, and what do I mean by this? Well, if I go right back to the start, when I read this semantics, I read it quite carefully. I said, when you're evaluating an add, you first of all evaluate x, then you evaluate y, and then you perform the addition. But again, that control flow is implicit in the text of that definition. There's nothing in that definition that says that you must evaluate x before you evaluate y. That's down to the semantics of Haskell. Okay? So you could, in another setting, maybe evaluate y first. So again, the process of calculating compilers is largely about making implicit things in definitions like this, making them explicit. So now I want to make the flow of control, or the order of evaluation, explicit. Okay? So let's think about how to do that. So a standard way of doing this is you transform your semantics into continuation passing style. So who here is already familiar with continuations? Stick your hand up. Okay, about half the audience. Who finds continuations a complete mystery? Okay, some people are not telling the truth. So continuations are something that people get themselves in a right mess about. It took me years and years to understand continuations, and then the light bulb went off, and it's actually a really simple idea. So the idea of continuations is that a continuation is just simply a function that's applied to the result of another computation. It just captures the idea of what you're doing next. Okay? So continuation is a function that's applied to the result of another computation. So let's have a little example of this. So suppose we are executing an addition, and we've got eval of x plus eval of y. If our computation, if the part we were doing at the moment is eval of x, then the rest of that expression is kind of like the continuation, and that's what we're going to do next. Okay? So the basic idea here is that we want now to generalize our semantics a bit further to make the use of continuations explicit, so that we're making the flow of control, or the order of evaluation, explicit. Okay, and we'll do this in exactly the same way as we did with the introduction of a stack. So we'll set this up as a little puzzle to solve, and then we'll solve it in exactly the same way by just turning a handle, and out the other side is going to pop a new definition. So let's understand the type here first of all. So I've got a new semantics here, eval double prime, which I want to calculate, and it takes an expression as input as before. But now the type has changed. So rather than going from stack to stack, it's going to go from continuations to continuations. And if you think about the types for a little bit, the appropriate type of continuation here is from stack to stack. You could generalize that a bit. You probably could go from stack to A for any A, but I don't need that generality here, so I've just got it going from stack to stack. So that's the new type. It's maybe a bit weird, but things become much clearer when you look at the equation which you want this thing to satisfy. Okay, so let's understand this. So eval prime, double prime, sorry, takes an expression and a stack, as we did before, but now it takes this extra argument, which is a continuation, and that tells us what to do next. And that's reflected in this equation, because what to do next is, once you're finished evaluating using the stack, that will give you a new stack, and then you just apply this function c to it. Okay, so if the type seems a bit weird, the equation should be straightforward. All we've done here is we've taken an extra argument, which is a function, and that function's capturing what we're going to do next. Okay, so all we do now is we turn our sausage machine, we turn the calculational machine, we do an inductive proof that this equation is true, even though we don't know what the definition of this function is, and out the other side pops the definition for that function. Okay, so calculation is not much of a spectator sport, so here's one I've prepared earlier. And let me talk through this, okay, to make sure everyone understands. Okay, so it looks a bit scary, but actually the definition is pretty straightforward to understand. It's very operational. So if we look at the base case, it says, how do we evaluate a value? Well, all we do is we push the value onto the stack, and then we invoke our continuation, because that tells us what to do next. And in the recursive case, how do we evaluate an addition? Well, you can read it now operationally from left to right. We, first of all, evaluate x, and then everything after that is the continuation that tells you what to do next. So once you've finished evaluating x, then you evaluate y, and then you perform an addition, and then you invoke c, whatever that was. And if you wanted to recover our previous semantics from this, that's very straightforward to do. If we want our previous semantics, which had type expert to stack, but now stack to stack is a continuation, so we can rewrite the type like that. If we just plug in the identity function here, which takes a stack and does nothing with it, then we'll get the same behavior. Okay, so the point here is we're calculating. We've got a problem we're trying to solve, and we've got a known thing. We've got the definition of this function, and we've got an unknown thing, and we turn the calculational handle, and we solve the equation. Okay? So the last step then is to get rid of the higher order functions that we've introduced. So if you think about where we started with a simple evaluation function, which was first order. It took an expression as input, a first order thing, and it gave us back an integer as an output, a first order thing. But we've actually ended up with a higher order function at this point. So why is that the case? Well, if you look at the definition for eval double prime, if you look at its type, the second argument is a continuation. That is a function from stacks to stacks. So we're taking a function as an argument here. And the result is also a function. The result is a continuation. That's a function from stacks to stacks. So what we've done here is we've started with a simple evaluation function, which is first order, and we've made the manipulation of arguments explicit using a stack, and then we've made the manipulation of control flow explicit using a continuation. And so we've got nearer towards a compiler, but we've also taken a step back because we've ended up with fundamentally a higher order program, which is taking both a function as an argument and delivering a function as a result. So the final step in the sausage machine is to eliminate this use of higher order functions. And we do this using a technique called defunctionalization. So another show of hands, who's familiar with defunctionalization? Okay, that's interesting. Far fewer than continuations. About half of you were familiar with continuations, so only a handful familiar with defunctionalization. Again, this is something which I found impenetrable when I was a PhD student, and actually, as everything else, once you actually look into it, it's actually really simple. So the idea here is when you're programming with functions as arguments, you typically don't use the whole function space. You just use a particular part of it. So, for example, if my arguments were functions from int to int, you don't use the whole function space, it's infinite, maybe you only construct functions of a certain form. And the idea of defunctionalization is you represent the functions that you actually need to pass as arguments using a data type, and then you interpret that data type later on. Okay, so it's a really simple idea. You represent the functions you actually need to pass as a data type, and then you interpret that later on. So how do we do this? So you can set this up in a calculational style, and I do that in the book and in the paper. I should have mentioned the talk today is actually based on one of the chapters in the new book, which I've got a copy of down there. I'll leave it lying around downstairs. And we've got a journal paper called Calculating Correct Compilers, which goes into all the gory details of this stuff. But it's pretty simple stuff. It's kind of undergraduate level stuff. So if you turn the calculational handle, here's what you're going to end up with. And I'll show you what happens in a few steps. So how do you defunctionalize this program here, or this semantics which we've got? So the first thing I'm going to do is make it a little bit simpler by making the stack argument implicit. And you can see at the moment, the stack argument's not really doing anything. If I look in this function here, I'm just bringing the stack in as an argument, and all it's doing is coming straight in as an argument on the right-hand side. So I could cancel it. Or if you want to be fancy, you could eta reduce it. And it's the same on the top. If I look at the definition of add, if I evaluate an add, I've got a stack coming in, and all I do is pass it along on the right-hand side. So I could cancel it again. And it's really the same in the first line as well. I've got a stack coming in, and if I introduced a little composition between the C and the push, I could cancel the S there. Okay, so let me make it a bit simpler. Let's cancel the S's. Okay? Nothing's changed. It's still the same types, still the same functions, but I've just written them in a slightly simpler way because that makes it a bit easier to spot where the continuations are. Because what I'm trying to do here is spot the forms of continuations that I need and then represent them using a data type. So the next step then is let me identify the forms of continuations that I actually use. Well, I actually only use 3 of them. So let me color these in yellow. Actually, it does show up on this projector. So I use the identity continuation to get things started, or actually it's really to halt things in the end. And then I use a continuation that does an addition of 2 things on the stack and then performs some other function C. And I have a continuation that pushes a number onto the stack and then performs some other computation C. So I don't need the whole function space of all functions of type stack to stack. I only need functions of these 3 forms. So the idea of defunctionalization is let's represent these 3 forms using a data type rather than passing around functions. So the last step here is represent them using a data type. So I will do that. And here's what we end up with. So rather than having a data type called cont, which is continuations, functions from stack to stacks, I'm now going to have a data type called code. And of course, you can guess why it's called code, but we'll come back to that in a moment. And this code data type has 3 constructors. It's got a constructor called halt, which represents the identity continuation, and it's got 2 constructors called add and push, which represent those continuations which we had on the previous slide. Okay, so all that's changed here is indicated in yellow. I mean, I've also changed the names of the functions because their types have changed as well. I've called them comp and comp prime. What are these functions? What actually have we got here? The hints in the name? Okay, we've got a compiler for expressions. Okay, so let's understand what's going on here. So this is a compiler for expressions which is going to translate an expression down to a sequence of pushes and adds terminated by halt. Okay, so let's understand the definition here. So our top-level compiler takes an expression as input and delivers us some code which is going to execute or evaluate that expression. And it does it in accumulator style. It's just like fast reverse. If you write slow reverse using append, it doesn't go very fast, so you rewrite it using an accumulator, and then it's faster. Okay, and it's the same idea here. We've got an accumulator which we're going to use to build up all the code which we're emitting. So this top-level definition gets things started. So what our top-level compiler does is it just calls our real worker compiler, which is actually doing the work of compilation, and it passes in the expression, and it passes an empty accumulator, which in this case, it's kind of like the empty list, where it's a nullary constructor. It just halts things. Okay, and then the actual compiler itself operates in the obvious way. If you compile a value, you just push that value, or you emit a push instruction, and then you have whatever code you've already accumulated. And if you compile an addition, you compile the first thing, so that will produce code for that. Then you compile the second thing, that will produce code for that. So you have 2 pieces of code kind of appended together, and then you emit an add instruction, and then you have whatever code you've already accumulated. Okay? So I put a little smiley face here, and that's my smiley face, because this makes me really happy, which is quite sad. So I like to calculate stuff, and I've spent my whole career calculating stuff, and written all sorts of papers about it, and various chapters and books about it. But the one thing I could never calculate in a way that I liked was this compiler. Okay, so this is, I mean, it's a bit sad. This is the end result of 20 years of work for me. Okay, it's three lines of code which I can actually calculate in a systematic way now. Okay, so let's just have a little example of this before we move on. So if I go back to my original expression, which was 1 plus 2 plus 3, bracketed to the right, and I run it through this little compiler, which I've now calculated by just turning 3 handles, then here's the code which I would get out. I mean, actually, there's a bunch of brackets here. This all nests to the right. It's like a list-like structure, but I've taken the brackets out so it's easier to read. So if you compile that expression, you'll get 3 pushes, 2 adds, and a halt. Okay? And we'll see in a minute how this is actually executed. So here is the new data type which we obtained by defunctionalizing the continuations that we actually need. Okay, so this new data type has 3 constructors, one called push, which takes an integer argument and then some more code, one called add, which just takes some code, and then halt. And the interpretation of this function is given by this little execution function. And this is really the semantics of this data type. Remember, what this data type represents is continuations. And a continuation is a function from stacks to stacks. Okay? So this is the semantics here. The execution function takes some code as input, that's a piece of data, and then it translates it down to a real continuation, which is just a function from stacks to stacks. And this definition just falls out of the defunctionalization machinery when you turn the handle. I haven't, again, shown you the calculation, but you just turn the handle, and this definition pops out for free. And it's very easy to understand what this does. So our little execution function says, if you've got some code, and the first instruction is a push, all you do is put that number onto the stack, and then continue with the rest of the code. If your first instruction is an add, then you pattern match on the stack, and it must have at least 2 values. You take them off, swap them over, add them, and then continue with the rest of the code. And then finally, if you execute a halt instruction, and you've got some stack, then there's nothing more to do, and you just return that stack. Okay, so what is this? What's another name for this? Any ideas? It's an interpreter, or a virtual machine. It's an interpreter for this little code language, but I think the more precise way of saying this is a virtual machine for evaluating expressions. Okay, so we've actually calculated 2 things. We've calculated the compiler, which translates an expression down to code, and we've actually got, kind of for free, the virtual machine, which interprets that code for us. Okay, and this is all just coming out from a calculational process. So let's just have a little example of this machine to make sure everyone understands how it works. So there's our example that we started with, 1 plus 2 plus 3, bracketed to the right. If we run it through the compiler, we get 3 pushes, 2 adds, and a halt. And now if we run this through our execution function, we can trace how it actually works. And it just does the obvious thing. So the first instruction is a push, so that will go into the stack. Then we have 2 more pushes, so they go into the stack as well. And then we have an add. And you can see now why add has to swap things over, because the 2 and the 3 are in the opposite order. So the add instruction will take the 2 and the 3 off, swap them over, add them, and put the 5 back on. And similarly again, you take the 5 and the 1 off with the add, swap them over, and then add them together, put the result back on. And then finally, you have the halt instruction at the end, which doesn't do anything, it just stops. Okay, which is why we've called it halt. Okay, so that's how this all works. So let's have a think about correctness now, because the title of the talk was calculating correct compilers. So I've calculated a compiler now and the virtual machine, but I haven't yet thought about correctness. So here's 2 equations which capture, in a very clear and concise way, the correctness of the compilers which we have calculated, and they're really easy to understand. So let's look at the first equation. So this is relating our compiler, our execution function, and our evaluation function. And it simply says, if you give me an expression E, and you compile it to a piece of code, and then you execute that piece of code using any old stack, what you will get back is that stack with the value of expression sitting on the top. Okay, so this ties together the 3 components in a very precise way. So it's tying together the compiler, the execution function, and the original semantics. The second equation just does the same thing for our worker, which is actually doing the real compilation. And the only difference here is that then there's some additional code which we've already accumulated. So we need to remember, when we stick the value of the expression on top of the stack, we've still got this accumulated code to run as well, so we need to execute that as well. Okay, so these 2 equations capture completely what it means for this compiler to be correct. And these 2 equations follow, or kind of fall out from, the defunctionalization machinery, or if you don't want to trust that, you can actually just verify these using very simple inductive proofs. Okay, so where are we? So let's pause for a minute, and then we'll do the last 10 minutes of the talk. So what we've got now is a 3-step process, or a 3-step sausage machine, for calculating a correct compiler from a high-level semantics. So the first step was we make the manipulation of argument values explicit by using a stack. The second step was we make the manipulation of control flow explicit by using a continuation. And then the third step was we make everything first order again by removing the continuations. And when you write it down like this, there seems to be some opportunity for making things simpler or combining things. So the first two steps just add two things in. So we add a stack and then we add a continuation. Maybe we could do that in one step. But more interestingly, the second and third steps seem to introduce something and then immediately undo it. Okay, so in the second step, we introduce continuations to make control flow explicit. And then in the third step, we get rid of them to make our program first order again. And these two transformations, people do these all the time in sequence. And it's bothered me for 20 years. Why do you introduce something to immediately eliminate it? And I didn't see for a long, long time how to get rid of this. But the question here is, can you combine these steps? And the answer is yes. Actually, you can take our 3 sausage machines, adding a stack, adding a continuation, and defunctionalizing, and you can bang them together, and you can have one sausage machine where you turn the handle and you get the compiler and the virtual machine in one step rather than in 3 steps. Okay, so what I want to show you in the last few minutes is just a flavor of how you do this. So the trick is really simple, and it's kind of embarrassing that I didn't see this. It took me 20 years to see this. The trick is you start with what you want. You start with the correctness equations. So I ended up with the correctness equations before. I turned these handles 3 times, and then I said right at the end, oh, I better check these things are correct. How do I know that? Well, that falls out of defunctionalization, or I can do a proof. But a better way to do it is start with what you want. These are the equations which I want my compiler and my virtual machine to satisfy. So the aim here is that I want to take these equations as my starting point, and I want to calculate all the unknowns. And this seems impossible because there's an awful lot of unknowns in here. If I give you these equations, all you know at the start is you know the expression data type, and you know the definition of the evaluation function, and you know the stack type. But everything else in here is unknown. So you've actually got 4 unknowns. So you've got the compilation function, the top level one. You've got the worker, comp prime. You've got the virtual machine, exec, and you've got the code data type. Okay, so you've got an equation here with 4 unknowns. You've got 2 equations with 4 unknowns. If you know some maths, 2 equations with 4 unknowns should be unsolvable. But actually, these things are so nicely kind of linked together via these 2 equations, it actually turns out to be possible to do this. Okay? So in practice, trying to calculate 4 interlinked definitions at the same time seems impossible. So I'd never tried this in the last 20 years because it's kind of you kind of look at these equations and think, well, I've got 2 equations, 4 unknowns. It's impossible. I can't calculate that. But actually, you can, and it's very simple. And the trick is, the experience you get from doing these things in a stepwise way just gives you just enough intuition about how to do this in a single step. So the kind of comment here is the experience gained from a stepwise approach, it turns out to be actually very straightforward to do this calculation in one step. And there's a few important points here. I won't go into the details of this, but the new calculation is simpler. And it's simpler in that we don't need any continuations anymore, and we don't need any defunctionalization. So half of you didn't know what continuations were, and most of you didn't know much about defunctionalization. So that makes this stepwise approach kind of not applicable, or you'd have to learn quite a lot of stuff to learn how to use it. When you combine all the steps, you don't need any of that stuff anymore. You don't need continuations, and you don't need defunctionalization. It's also more direct as a calculation, because I'm actually starting off with what I want. I want to calculate correct compilers. So a very natural starting point is to start with the correctness equations and actually calculate from them. So I'm calculating from the goal which I eventually want to solve, which is to satisfy these equations. And interestingly, when you stare at it, if you look at the calculations in the paper or in the book, the calculations have exactly the same structure as the stepwise ones. Okay, so this was quite interesting for us. We actually wrote a Journal of Functional Programming paper about this about 2 years ago, and our original paper was 100 pages long, which sounds ridiculous, but we had all sorts of different language features in there in our combination, and then we discovered how to combine the 3 steps, and the paper shrank to 46 pages. So we've got a factor of 2 shrinkage, but more important than that it's a lot simpler. You don't need defunctionalization, you don't need continuation. All you need is simple equational reasoning, nothing more. So that's more or less what I want to tell you. It's just kind of an introduction to the idea of calculating correct compilers. So I've got two slides left now. So just to kind of stand back and summarize, what we've got here is a purely calculational approach to developing compilers which are correct by construction. So by correct by construction, I mean that once you get your compilers by this approach, you don't need to prove them correct because they're correct by the way that you make them. Okay? It only requires simple techniques. No fancy types, no fancy machinery, just simple equational reasoning. In fact, all you need is what's sometimes called the holy trinity of functional programming: recursive types, recursive functions, and induction. That's all that you need here. And the interesting part is that this actually scales as well. So I've shown you it, or shown you a flavor of it, for a very simple language, simple arithmetic expressions, but we've tried it for all sorts of other languages as well. We've tried it with exceptions, with state, with variable binding, exceptions, interrupts, all sorts of stuff, and all sorts of combinations, and it just worked, which was quite surprising for us. We thought, this is too simple. It can't work for more sophisticated settings, but it actually does. And you can rediscover interesting compilation techniques from the literature, and actually you can discover new compilation techniques. We discovered one or two new ways of compiling things where there was kind of interesting interactions between different language features. Something which is interesting as well is the specifications become even more open when you consider more sophisticated languages. And in fact, you end up with the idea of partial specifications. And I'll show you what I mean by that. So if I go back to these two correctness equations now, which are quite simple, and I think, well, suppose I extended my language with simple exception handling. Suppose I put a throw primitive and a catch primitive into my language. What would I need to do to modify these correctness equations? And in particular, what do I need to do when something raises an exception? So if we look at the first equation, this may be the right equation when E doesn't throw an exception. If E doesn't throw an exception, we just want its value on top of the stack. But if E throws an exception, what are we going to do? Well, here we've got a choice to make, and these choices are what we want to fall out of the calculational mechanism. I don't want to presuppose we're going to use stack unwinding or some other way of implementing exceptions. I want to calculate that and have it fall out of the mathematics. So what we end up doing is sometimes you don't know even how to write down your specification because I don't know how to modify that first equation to deal with the fact that evaluation of E may fail if it's a language with exceptions. So I end up with partial specifications. So you actually end up evolving the specification as you go along as well. And this seems like something that just shouldn't work. You've got an equation with 4 unknowns, and then you actually have even another unknown component. You don't even know how to write down the specification. And as you turn the machine, you reach a point where you need to make a choice. And then maybe you've only got one way to go, and you pursue that. But sometimes you have a choice of 2 ways, and you pursue that. And that's how we ended up discovering new compilation techniques. So sometimes you go down a path and you find, oh, we just end up with stack unwinding, for example, or you go down another path and you end up with a different way of compiling these things. And that was quite interesting for us. Okay, so final slide, ongoing work. So everything which I've told you is about stack machines. But of course, real machines are register-based, so we're very interested about how we can modify this approach to register machines as well, and we've got some preliminary work about that, which we're planning to write up soon. We're also interested in more realistic languages. I mentioned GHC at the start, and maybe some of you thought, oh, he's going to calculate GHC. That'd be a very ambitious thing to do. But what we'd like to do is kind of scale this to more realistic source and target languages. So maybe we can calculate a compiler for GHC core, or maybe we can calculate a compiler for a mini version of C. And if we look at the backends, maybe we can calculate a compiler which targets a particular machine architecture or something like LLVM. We started to think about this. We've also started to think about mechanical assistance. So at the moment, the sausage machine is me and Patrick, my co-author. I do it on pen and paper. He does it with the assistance of a proof assistant. But what we find is that most of the steps in turning this handle are you just do the obvious thing until you get stuck, and then you need to make a choice. And if you make a choice, we typically explore all the choices which you can make. And so this is something which is very much right for mechanical assistance. We'd maybe like to have a tool where you feed in your semantics and you say, okay, there's my correctness equations that I can write down so far. Do your best with them. And it will kind of turn the handle until it gets stuck, and then it will ask for our input again. And our feeling from doing quite a few of these calculations, we've maybe done a dozen of these calculations, is that it's feasible to actually mechanize this. And the final thing I'd say is we're interested in putting together a funding application to kind of scale this up to more realistic languages, so more realistic source and target languages. And we're very interested in talking to people from industry. So many, if not most of you, are from industry. If this has sparked your interest, if you've got a little language in your company that you need to compile very efficiently, or maybe you even don't know how to compile it because it's got interesting interactions of language features, I'd be very interested in talking about you because we're looking for partners on our grant. We've got plenty of academic partners. We've got a few industry partners lined up, but we're interested in people who've got interesting computational problems that maybe this kind of technology could help to solve. Okay, that's it. Thank you.
Okay, so you've described a process where you put in an expression and outcomes code.
Yep.
Maybe a silly question. What happens when you put in code as the input? What happens if you view code as the expression? Do you get out code again, or do you get out something different?
Ah, that's a good question. I haven't thought about that. That's a good question. So you're saying if you just apply exactly the same methodology starting with the code, what do you get? I thought initially you were saying, could you reinvent the semantics that the code came from? But no, I don't know what would happen.
No, I'm wondering if it's the identity function in that case.
It's a good question. I don't know. Good question.
Okay.
Yeah, it seems like the intermediate goal of your work is to put compiler writers out of a job, and the ultimate goal is to put computer science professors out of a job. So I just wanted to know, have you thought this one through?
Yeah. So the goal for me is to be able to have a principled way of discovering things. I mean, compiler writers are really clever people, and what I've found over the years is clever ideas are often based on mathematics, and maybe that's not initially obvious, but the more and more you stare at things, if you look at kind of very clever optimizations which are used in things like GHC, when they're finally understood, there's a very simple mathematical model for what's going on. And that's really my aim here. I mean, compilers are complicated things, clever people work on them. And what I want to do is kind of have a principled way of discovering the clever things so that you don't need to be Simon, basically. I'm not trying to do, not trying to do people out of jobs.
Any more?
Yeah, so you said, well, I'm not going to show you Haskell right now. We're going from Haskell to a machine. But let's say you do, like, if you look at, for example, GHC now, there's lots of intermediate languages in between where the optimizations happen. But if you apply your technique, we immediately end up with a stack or register machine without the optimizations.
Yeah, so
how do you envision the...
Yeah, so I should have mentioned that as part of ongoing work as well. I mean, there's nothing about optimization in here at all. I mean, you'd end up with a simple implementation, actually, which is sometimes quite efficient already for different combinations of language features. But then you can think, well, how could I optimize that? We're also interested in calculating optimizers. We want to calculate everything, but I mean, yeah.
All right, thanks.
That's a good question.
So towards the end, you said, oh, I've shown you X, but there's a much easier way to do it with this more direct approach, right? So why did you show us the hard way instead of showing us the easy way?
I'll tell you for why, and we do this in the paper as well, and we very carefully articulate this. If we show the direct way first, it doesn't make any sense. It's hard to understand.
Oh. Simple, but hard to understand.
So there's a few tricks in there about how you actually structure the calculation. So it uses simple techniques, but the kind of mindset about the way you calculate, you need to kind of see how these things fit together. If you do the stepwise approach a couple of times, you see the tricks, and once you've seen the tricks 2 or 3 times, they're the same. But it's hard to see it's hard to explain it without seeing how to do it the more complicated way first, if that makes sense. So I see your point. You're kind of saying, well, he's claiming it's simple, but is it really so simple? It's simple once you've seen the kind of stepwise approach, and then you see the tricks. And then it's the same tricks again and again and again. I mean, the devil's in the detail here. I mean, that's why, really you need to read the paper or have a look at the book chapter to see how this stuff actually works. I just wanted to give a kind of high-level flavor of how it all fits together.
I was just to say, is it going to put the link to the paper up on the projector again?
Yeah, if you search for that title, if you search for calculating correct compilers, there's a PDF which is not behind a paywall. It's on my website. Just search for the title of the talk and you'll find it.
Thank you.
Okay.
So yesterday we had a keynote by Don Stewart, and he was saying something that I also experience quite a lot and are also telling to other people, namely that in Haskell programming, when you're looking at it in the right way, almost every problem is in a way a compiler or interpreter problem. You're translating one small language into another, and essentially you're using techniques that are corresponding to interpreters and compilers.
Yep.
So do you have any thoughts on how these techniques might help in a situation like that, where essentially you have a source language given and perhaps a specification in Haskell, but you also have a target language or an API given that you want to express the same semantics in?
So it just cuts down the search space. I said when you're calculating from these 2 equations, there's 4 unknowns, and one of the unknown was the code type. But you could fix the code type yourself, if that's what you're saying. It could be a particular architecture, and that just narrows down the kind of design space a bit. And we've experimented with that, and that, I mean, with simple languages, and that works as well. But what we want to do, I mean, it's work for kind of simple features and combinations of those simple features, but we really, the killer thing to try now is actually, can we make this work for more realistic practical languages, front ends and back ends?
What's the lowest level backend you tried? Have you tried compiling it down to hardware?
My co-author Patrick has, so I think he started to think about compiling down to kind of FPGA type stuff. But that's one of our back-end application areas we want to consider. So if any of you in the audience have experience with kind of hardware FPGA type stuff, we're very interested in talking to you if you're interested in compiling in a principled way down to that kind of stuff.
So it's not yet in the paper?
No. The paper is just about stack machines. It's already 46 pages. We thought that was enough.